All right, I think we're ready for another exciting embedded microcontrollers class. Yay! Let's see. Tonight, I think we've got a homework 10, which is due. Are there any questions about that? This is our last class prior to the break. After the break, we're going to have a homework 11 due. And I thought maybe what I would do is go over homework 10 if anybody had any questions. Any questions about homework 10? No questions? And then I would go on to homework 11. Are there any questions about homework 11? We didn't quite cover the whole thing last time. Any questions? Should I look at it? Open it up? Just quickly sort of scan through it, see if there's any questions. Homework 11, I think we looked at all the questions up to something like, was it 19 or something like this? I forget now. 17. We got all the way through. And let's see. Talked a little bit about the layers and IP addresses and server sockets. I think I gave you my little demo video for implementing a telnet server and a web server. And let's see now. We're up to, I think this is question 19. This might be pretty close to where we left off. Any questions about this? Network sockets. I guess we kind of touched on it a little bit. No questions? Just sort of thumbing through here. So I'll ask you a question then. Under what circumstances does server.available return? Anybody know? When will the left-hand side of the equal sign yield a client? I'll give you a hint. You don't get a client until the right-hand side returns. True, right? Yeah, no, it returns an instance. Under what circumstances will it return an instance of an Ethernet client?
If a server is available?
Yeah, it has to make a connection.
Right.
It has to make a connection. So this is coming in for incoming clients, right? So you're running the server, you do an available, you're waiting. This is stop and wait protocol until somebody comes in and connects with you. Once they connect with you, then you have to service that connection. So when you're an Ethernet web server, you use your server instance to determine if someone's attempting to connect to you. Once they connect, you have an instance that represents the client that is connecting to you. I don't know if that's obvious from this code. So with that client, you should be able to obtain a socket. Now, here's the next question. Does the socket allow you to have an input stream or an output stream?
Input, right?
It's a trick question given by a sneaky professor. The answer is both. You have to be able to communicate with the client and listen to the client. So the client's going to give you a query, going to try and get some sort of file, I imagine, with hypertext transfer protocol, and the file might be something of the form of an HTML file, and you will have to look at that get command with the file name, might be something like get index.html, and then you will have to either generate or retrieve the index.html and pump it out into the client. So that is the way servers work. And so and you can do this on your Arduino Uno. Your 8-bit toaster controller can absolutely run a web server. I know, I've done it. So when you've got an instance, and they do, by the way, socket servers in Java do exactly the same thing, only they typically launch a thread every time a new connection is made. Here in the Arduino world, we're not trying to do anything multi-threaded. Not that it's impossible, but it's, not what we're trying to do here. So here's another sort of example. We've got our little Ethernet server coming in right to port 80. So whatever IP address we have, in this case 192.168.1.177, we're listening on port 80 in the Arduino. And then the Arduino is going to presumably have some client that connects. And once you have the client available, you'll be able to read whatever it is the client is writing. And then you're going to write back to the client, and you're going to say, hypertext transfer protocol, blah, 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 blah. Text HTML is on its way. This is what they call a multi-purpose internet mail encapsulation or mail extension. I forget which one it is. I think it might be extensions. So what you can have is SND/AU for an AU type sound file, or text/RTF for an RTF style text file, assuming the browser is equipped to decode it. It may not be. And then RTF is rich text format, which is, for Microsoft Word. And then you close your connection. So they stopped and waited for your response, and no throughput occurs until you respond. So if your response takes a long time, throughput goes to 0 real quick. And here's something where someone's saying, oh, look, I'm going to output HTML, and I'm going to do an analog read and figure out what the value is from each one of my channels. And I will print out analog input and the actual value of the sensor with a new line. This is a break. And then after I'm done, I'm going to terminate the HTML. So in other words, I'm synthesizing HTML as I go. There is no actual web page. I'm generating it in real time, well, in however much time it takes me to pump out like some HTML into this client. And when I do a client.print, it's going to the output stream. That's a print stream. So if somebody types carriage return, you start a new line. If they have, well, let's say this would be a line feed. This would be a carriage return. If it's not a carriage return, you've got a character in the current line. And that's it. That's your web server. It just pumps out values from the ADD converter every time somebody hits enter. So that's kind of cool, building a web server. Let's see, what else do we need to know here? You guys know what subnets are and gateways? You probably do. The gateway, that's going to be like your router, and that'll be the thing that gets you out to the internet. Subnet, that's going to give you a mask, which allows you to mask the traffic that you may or may not be receiving. Is port 24 a common port for Telnet? You can certainly look it up. There's several ways to do that. You could go to services and look up port 24. And it says mail service. Wow, mail service. And what's he asking? He's saying it's the common port for Telnet. Well, it doesn't look like it. What could it be? So let's find out. We have more services, or cat services, and pipe it into a grep on Telnet. And it's port 23, not 24. So that looks like a false. I'll check it against the answer key just to be sure. And yeah, I'm correct. So you don't have to remember these things, just look them up. Let's see. Here's a MAC address. We know what subnet masks are. In my case, my DNS service is the same thing as my router. My gateway is the same appliance as my router. My personal IP address for the Arduino, I've statically assigned it. I'm not using DHCP on the Arduino as a client, which is dangerous because if you keep statically assigning these things, you're bound to have a conflict, and that can take down the whole local area network. Now here comes a server on port 23. That's the common telnet port. Now you can reuse that for anything you like. You know, you're the programmer, you can do what you want. But if you want to be consistent with the rest of the world, port 23 is the common port for telnet. People expect when they see an open port 23 to be able to telnet to that port. That's both good and bad, right? Because the script kiddies can come in and start guessing passwords. And the scripts are able to go through many dictionary passwords very quickly. So let's see now. What do we got? So there's client available, server.available, giving us an instance of a client. And if we got a client, then what we can do is we can pump out data to the client with print statements. And that's it. That's your web server right there. So here's something that says, the following code is writing a new line every time it reads data, but that should not be needed given the prior telnet server code running on the Arduino. What is he talking about? Well, now let's see. Here comes the socket, right? Host and port number. And then he's going to get the output stream. So this looks like a telnet client being written in Java, right? It's hard to tell, right? But it's actually, when you look at it and you say, oh, look, there's a buffered reader. Yeah, that's Java. So now here comes a Java client on port 23, and he's trying to connect to host 192.168.1.177 on port 23. So he's connecting to the Arduino, and he gives you a socket, and then he takes that socket and he says, let's get an input stream. And I get both, right? I have an input stream and an output stream from a socket. But let's start with the input stream, create an input stream reader and then a buffered reader so that I can do things like br.readline. And now I'm going to go and get the socket's output stream and make a print writer out of it so that when I do out.print, it goes out to the socket. So this is communication network programming right here. And what we've done is we built a telnet client that can now talk to the Arduino. And you don't normally program Arduinos in Java, but if the Arduino is using the Ethernet as a substrate in order to be able to isolate complexity and the embedded hardware implementations, then you have a mechanism whereby you can write in any language you like. Write it in Python for all I care. Write it in COBOL. Well, don't write it in COBOL. You could write it in COBOL, but don't do that. And then, because it's like really ancient language. I took that course like in the 70s. But anyway, yeah, don't write it in COBOL. And then let's see. This will print out ready. It'll print out a new line with the print line, out.print line. And then it's going to read from the Arduino whatever data is being pumped into the telnet's output stream. And then it says, is this true or false? Do I need to print a new line every time I read data? What do you think? This is question 30. You guys didn't ask me to go over this, but I am anyway, so there.
Would it be false?
That's right. Why is that?
It's because of the
Let's look at this prior code that we're talking about here.
Yeah, client
Here's
dot connection.
client connected. Yeah, we want client
Yeah.
connected to return. And so you need a handshake with the Arduino. Without the out.print line, the Arduino code client connected will not return. So I need that. I need to connect. I need to have something come back, and doing the print line will help me to get a connection so that I can proceed. So whenever I get that connection, I want to come in and do the out.print line so he knows I'm there. I'm connected. Otherwise, it will not return. And I think I gave you guys a demo of how this was doing two-way data communications,
Mm-hmm.
where it was printing out X and Y. So this is doing the similar thing. This is taking the strings that are coming in a read line, which are comma separated strings. So it might be something like 29, 30. So this splits along that comma, gives us an array of string, which will give us the 29 and then the 30. And then we'll parse that, turn it into an int, and then we can basically just print it out, 29 space 30. So the comma was converted into two separated values of ints. If the strings can't be converted, it returns zeros. Well, what happens if you do integer.parseInt and you type in quote bleh? The answer is you get an arithmetic format exception at runtime. In other words, you can't say, please type in a number and then type in bleh, because the computer will go bleh. That's my computer science explanation of how that works. Right? In other words, if you say, type in a number and you pass it into integer.parseInt and it looks like bleh, and it's not a number, the computer's not going to like that. It's just going to give you an arithmetic parse exception at runtime, which you can try and catch or not. And if you don't, it'll stop the thread of execution. If it's your main thread of execution, your program dies with an exception because the format's not correct. You can build more robust parsers than parseInt, but that's what parseInt does. And I think I showed you guys how you could move the mouse with a couple of potentiometers, and we were moving X and Y and up and down. That's what the AWT robot does. So AWT robot allows you to support mouse move so that when data comes in, you can move the mouse around. You don't need HID protocol for this. That's Human Interface Device Protocol, which is normally used for a mouse interface. Instead, what you do is you go to the serial port and read the data that's coming in, and then use that invocation of move, and that will move the mouse to wherever it is you like. What else is in here? And that's it. That's homework 11. Are there any questions about homework 11? No questions? Really?
Yeah, thanks for going over it, Professor.
Sure, no
Appreciate
problem. I can go back over any question you want. You've got the whole break to work on it, but there it is.
Thank you.
And this is being recorded, so you can look at it again. So then
I have a question. When is it going to be due?
I believe it's due on the first Thursday back from break, which if I go to the beginning of this thing, there. Homework 11 is due 12/30/20. The final lab project is due 12/9/20. The last day of class is 12/10/20. And then we're going to have the final on 12/17/20. And so this is kind of a compressed view of the rest of the semester for two classes, because the second class, the lab, that's where your final project is coming in. And I was going to give you a little discussion about the final project, unless you have questions about the dates. If the dates look okay, I'm going to proceed. Any questions about the dates? It's all part of the grand lesson plan that I have here on my little pad. So I'm thinking you guys might have some questions about the project. So I did the project. How about that? So here's my solution to the project. And what I'm going to do is I'm not going to bore you with the long lecture that I've prepared. Instead, I'm going to give you the demo. So here's the demo. Let's see if this works. Can you hear that okay?
Yes.
Yeah.
Yeah,
Okay.
dialing.
It's dialing. Yeah. So now what happens when you program a project like this and you listen to it dialing while you're debugging it is it drives you mad. I'm sitting here listening to this thing dialing and I'm going, man, why don't we shut this thing up? But I have to keep it on because I'm debugging. And so I'm sitting here listening to this thing. So if you're going to do this, close the door, make sure nobody else is listening because they're going to just come in and go, what the hell's the matter with you? That's going to be, they're all going to get crazy. And so that's my warning about this project. I didn't realize how annoying it was, but this is like a really annoying project.
If we put a potentiometer just to control the volume, what resistance would you recommend?
No, I don't know. I guess it would depend how the resistance maps to the frequencies. I was going to give you a little discussion about that. So, this is one of those things where I think maybe the software engineering needs a discussion. So let me show you what we've been doing, like you mentioned, with the frequencies. Okay, so this was an oscillator that we used for one of our labs. I forget which one exactly, and I think I can turn up the volume without driving myself crazy now. And I'll turn it up a little more so you can hear. Can you hear that okay? So that was one of our labs where you were generating an oscillator waveform. And so what we had in here was everything in one big main, which was, a bunch of functions, a loop, a bunch of setup stuff, and kind of crummy software engineering, I thought. A way to fill up a sine wave, maybe a timer in the back that was kind of running on interrupts to chug out samples to this little SPI DAC, and that was for the MCP 4921 DAC. And I looked at this code and I said, there's nothing good about this code. I mean, other than the fact that it works. So then I said, well, let's change it up a bit. So I decided to make a little DAC library. And in my little DAC library, I made an instance of a DAC. And, you can parameterize these things. Like, for example, I could have said, well, let's put the chip select in there and maybe changed its behavior somewhere else, but I didn't do that. Instead, what I did was I made a little .h file, said I'll have a DAC, it'll have a setup, which will be just like the setup over here, right? It does all this SPI stuff and the port thingy, and we'll just sort of set up our chip selects and our LDAC. And if you wanted to kind of get an idea of what's going on, it might be a good time for you to sort of grab the MCP 4921 data sheet and just have a quick looky-loo at what's going on that. I think it's going to be this thing here. Just a minute. Yeah, there you go. So then if you're wondering, what's up with the chip select and what's up with the, can I zoom in on this? There's got to be a way to zoom. There we go. So then I wanted to say, there's this LDAC, it's inverted. There's this chip select, it's inverted. the whole thing looks kind of like maybe LDAC and chip select are needed. And what does it do? And then it says something about loading the DAC. So this is the not load DAC pin. This is the chip select pin. And somehow all of this is wired, right, to the Arduino. And we have to know what pins go from the Arduino to the chip. So in other words, pin 5 on the chip is meaningless to you as a programmer unless you know what wire on the CPU pin 5 is wired to. Same thing for chip select. So if you want to select this thing, you'd better know what pin it goes to. And we can know that, at least in part, either by looking at the schematic or by looking at the code. So if we try and find something like the chip select, we should be able to find that in here somewhere. And there it is. Here's chip select and there's LDAC. And those are pins we have to set up as output that we need to toggle, you see. And so that's important. So that's the CS chip select and the LDAC, and they're both on an inverted form factor. And so here we can see chip select and LDAC are both set up as outputs. And we're going to end up, toggling those things. So this is actually a way to manipulate one of the pins, one of the bits in the data direction register. And so when you look at the Arduino, you're going to wonder, well, where's pin 8 and where's pin 9 on the data direction register? And, there's a couple ways you can go on that if you're, are actually wondering what pins are which. Here's the Arduino. Here's the pins. There's 8 and 9 coming right out. These are digital I/O pins. So you can see that's probably where the DAC is wired. And if you're ever wondering, you could always just use a continuity checker and make sure. Sometimes we have new hardware coming into the lab and we don't know how it's set up. And I always encourage people to check how things are wired, especially since you're coming up with shields that may be made by third-party vendors who are selling on eBay for as cheap as they possibly can. And we revel as customers in the very inexpensive shields that we can purchase in the Arduino ecosystem. And having done that, we then curse ourselves because we saved $2 and ended up getting a completely undocumented piece of poop. And we're like, holy mackerel, this just set me back a weekend, but I saved $2. And I'm like, yeah, that's the way it goes. So you really got to check this stuff. And one of the things you can see when you go to these different pin numbers is they somehow map to pins on the actual 328 PU. I think we said it was going to be pin 8. There's digital pin 8, and that's on port B. And then somebody said digital pin 9. Well, that's also on port B. And see how it says port B0 and port B1? Well, that's kind of important, right? Because you're going to be writing to the B register if you're going to write these things directly instead of one pin at a time. So you can set them both to 1, 1, or you can set the least significant bits to 0, 0, or whatever you like. And that's going to essentially allow you to manipulate this port B. So when you're looking at, for example, this code, and you see something like, okay, somebody says port D, and someone over here says, oh, look, here's port B. And it says pull chip select high, port B. Well, look, he's coming in on port B, pin 0, 1, right? So now come back over in here onto this chip, and here's port B, and that's digital pin 9. Well, digital pin 9, if you go back to the code, and this is like how people program, right? I mean, this is, kind of wacky. Pin 9 was supposed to be a chip select, I think. Yeah. So what you could have said here was pin 9 maps to bit 1 on port B. So you could just as easily have said bit 1 on port B. And over here you could say this is bit 0 on port B. I guess you can uppercase it if you like. And so I could write, I can do a couple, I got a couple of ways to go. I can either write a high out to port pin 8, right? And then write another high onto pin 9, or I could write 1 1 out to port B. Right? And so when you see something like this, 1 1 is going out to port B. Here it says not 1 1 or 1 1. So what he's doing is he's taking whatever is in there and he's going to set the least significant bits 1 and 1, which means he's going to set chip select and the load DAC both to the default high state. And that's what it says here. Chip select and load DAC are both going to the default high state. See this code? This code is not obvious, right? I mean, could he have done it a little bit better? Oh, sure, right? He could have done a digital write equivalently. Digital write. And he could have said pin 9 to high. And then he could have done another one, digital write for pin 8 to high. Right? Then you could take this guy, comment him out. And in fact, if you really wanted to do it upright, you would call this chip select, because that's what it is. And you would call this LDAC, right? Because that's what that is. And now you have essentially done the equivalent thing. And when you read this code, you don't know that. You can't know that unless you go back and you take a look at the stinking chip and you go, oh yeah, this is port B, and here's the least significant bit for 0, and here's the least significant bit for 1, and that's how you set pins 8 and 9, and do them both at once without having to do 2 invocations to digital write. And then after making that substitution, then what do? And the answer is, well, you have to test it. So now you got to upload it again, make sure there's no errors, no compilation errors. And then you got to get your speaker on again. And so that's all working. So now we've, have we slowed anything down? And the answer is, yeah, in setup. And how much did we slow it down by? I don't know, 10 cycles or something? What difference does it make? It's in setup. So I say, this is one of those things where sometimes it's better to just make it more readable than to, I don't know, proceed to make things look kind of efficient. This is efficiency versus readability. So having said that, right, you can now go into the DAC CPP. This is the code that I started writing out. And you can see there is a setup in here, and it's part of the method which we call the constructor, which returns nothing, not even void, but has the same name as the name of the class. So having, separated out the DAC setup and the header file, what that means to me is I can reuse the DAC code elsewhere. Moreover, this little code in here we've just discovered can be rewritten in a way that is perhaps, I don't know, more readable, somewhat more readable, a little bit more readable. And then that kind of makes it nice. And what we can do to make sure it still works is we can go to our little generate code, and I guess we're going to have to listen to this thing again. Can't be helped. And by the way, I'm having to reset my Arduino each time, and I don't quite know why. Okay, we got to turn that off now because I've been listening to it all morning. So that was kind of an interesting thing. That right there was a little lesson, right? And how to do these kinds of controlling items. And that's all in the setup, but instead I moved it from the setup to the constructor. So that's good. And then there's other stuff. I mean, like if I knew there was going to be different DACs, I might like to change chip select and the LDAC pin if I was going to add more DACs. And so that might be something I'd like to put into the argument to the constructor. But the way I built the shield, there's only one DAC. And so I can just do what I want, kind of. And let's see, what else do we have? Chip select is equal to pin 9. Of the MCP 204921. So anyways, so that's good. I like that. It was a very nice way to go in terms of explaining why things are the way they are. Let's see, what else do we need to know about the DAC stuff? So here it is again. Here's port B. And here it says pull chip select low. Now, would it have made sense to call digital write? I don't know how many times. 1, 2, 3, 4, 5, 6, 7, 8 times in order to set the port and all the pins on the port? And the answer is no. That would not have made sense. So what we've done here actually was a far more efficient way to go. And we can kind of see how that made life a little bit easier for the computer. So at this point now, we're really down into the bit flippy part of writing out to port B. And if you go back and you look at the chip layout and you look where port B is at, you can see port B is actually distributed in several places. But if we start with port B0, port B1, port B2, 3, 4, 5, and then it jumps all the way over here to 6, and then goes down to here to 7, it's kind of all over the place in terms of where the pins are. I'm never sure why they put things where they put them, but that's what they're doing. And so that's a, that's your guide as to which pin numbers map to which bits on the port, which is, once you know that, that's how you're able to set up the binary outputs on these things. And so that's how that gets programmed. What's a NOP? What's that? Here's some things. ASM volatile NOP. What's up with that? Do we even need this? Can I comment it out and will things still work? I don't even know. Compiler likes it. I guess that's not a good measure of anything. Let's turn it on again and see what happens. So that seems to be working, right? But that NOP, what is that doing? Is it's giving you a small delay, no operation, where the CPU sits idle as you flip this bit from 0 to 1. And that is all it does. That's what it does. So that's a...
It could be useful for reading the output, right?
No operation, doesn't read anything. It doesn't write anything. It just sits there and cycles a little bit of CPU time. As when you write, you may be exceeding the time it takes to get a reaction out of the DAC. So you want to load the DAC. You want to give it a little time to load the next number. That's what this ASML is for. This ASM assembler. And so this no-op, that's actually the symbolic assembler machine instruction for no operation. And, no ops on a microchip, I'm not quite sure how many cycles they take, but they're pretty fast. So now how do we use the whole thing? Right? Does it appear here in DTMF generate? And the answer is no. No, that's a level of abstraction away from the DTMF code. As a matter of fact, I don't think I need this key anymore, because what I did, and this is actually not a bad thing to look at, so we'll look at it. I wrote a little loop, and I added numbers and the star and the octothorpe and ABCD. And I could have done it a couple of ways. I could have made an array with individual characters, but I'm kind of lazy when it comes to typing. So I just said, let's make a string with all the things you want in it. And so if what you wanted to do was have all the characters that you wanted to recognize, I just set it up as a string. Then I did an s.length because I didn't want to, I'm too lazy to count the number of characters in the string. Plus, I might increase the size of the string. I don't know. I could probably do something like this. 203, 555, 1212. And I don't know what else to put in. And if I do that and upload, it should be able to handle anything you want to put in there. And so in some sense, it's a better interface, right? Because you can put in any dial string you like. And what I'll do here is there it is. And we can dial faster if you like to dial quick. I don't know what this will sound like. I've never tried it. Isn't this fun? I think this is very fun. What a fun thing, you know. So we'll hit reset and see what happens. Okay, yeah, I'm gonna guess that the phone system is not gonna dial that for you. That's really fast. We'll have to slow that down a little bit. Most phone systems will just cough at that and they'll go, what the heck is he doing? Of course, if you wanted to really increase your data rate, that's probably not a bad way to go, right? Let's slow that down a little bit. Even that's probably a little bit too fast. But still, I mean, it's cool. It's cool. The duration of delay and the duration of the tone have been made the same. But in fact, you could probably increase the length of the tone by somewhat. And then I think it might be perhaps decodable by the phone system. Maybe. Right, so that's got a 50% duty cycle on the tone versus the duration. Or is it 50%? No, actually, it's more. Duration of the tone is twice as much as the duration of the delay between the tones. Anyways, there you have it. So that's not a bad interface, I guess. And then I use the s.length to get n, gave myself a character array and converted the string to a character array, because when I did my generation, I just do generation one character at a time. That's my generation thing. And I modified the generator a little bit. Not too crazy about the generator code right now, but it's all right. I mean, it does what it does, and that's it. So let's go through it a little bit. So what I did was I added A, B, C, D. Okay, so right here, this kind of doesn't make a whole lot of sense to me, right? I mean, in other words, if you did this and you said, well, let's make, instead of 48, let's put in, 0. That should work, right? I mean, you shouldn't have to put in the ASCII, right? I mean, where do these numbers come from? That's a good question. Okay, so these are all ASCII codes. So if you were to, let's see if we can get up there's usually an ASCII table available for the asking around here. ASCII table. So let's take a look. Here are the ASCII codes, extended, decimal, right? So ASCII code for 9. What did he do here? He gave it to me in HTML and binary? No. I want the ASCII code in decimal. Shoot. This looks right. So let's look up 9. Here's 9, and the ASCII code in decimal is 57. Is that no? Yeah, 57. So if I go over here and I look over at 9, sure enough, it's 57. But why am I typing that stuff? I mean, it's going to come out to be the same as if I did this, right? I mean, there's no material advantage to putting a literal in when and encode it in ASCII when in fact you can just type it like this, right? So that's kind of, I don't know, bad software engineering, something like that. And your case statement will certainly take a character, any static literal embedded as a scalar into the case statement is fair game. And certainly individual characters like this are fair game. And not to put too fine a point on it, I'm going to stop now because going through the rest of this is a routine engineering exercise. I'll just run the code again, upload it, and we'll see that it still runs. I hope. Let's see, let's turn on the speaker. So there it is. It's still running, doing its thing. So there was no reason that I could see to encode these things in ASCII by hand. I mean, why would anybody do that? So here is character A is supposed to be a 65. If I go to the ASCII table, I can certainly look it up. But isn't that what compilers are for? I mean, no kidding. So here's 65, and yeah, that's an A. Okay, I get it. But why is it being typed here? I mean, this is in this guy's library. We're professionals. This is how professionals do it. I have no idea. I mean, this just sounds, in retrospect, this looked a little bit boneheaded, but listen, it's somebody else's code, so what the hey. So as we go through this, then we say, okay, we wanted to add A, B, C, and D on this. And then the question was, well, what are these numbers? What's all this stuff for? 14, 15, 17. Anybody know what that is? What's that, 14? I understand row 697, right? Because what? Because I can get my touch tone frequencies, right? DTMF wiki, get my dual tone multiple frequency signaling done for the phone system, and I can find that stuff, right? It's all online. There it is. And then it says 1633. That's one of the columns. 1209. That's another column, and I can look that up, right? I mean, here it is, 1209. 697. That's down here. That's the first row. So then, well, what's the 14 for? What's that about? Where'd that come from? 33, 30, 27. Is there a pattern here? What's it mean? Well, the answer is you kind of have to look around a little bit and figure out, well, there's this wavetable here, and he's being clocked out at a frequency, right? And it's a regular frequency, and you can find out what the frequency is. You can read the directions, he says he's setting the timer to 10 kilohertz, and we can learn how to do that ourselves if we want. But before we get into the lecture on timers and refreshing ourselves on timers, if he's clocking this thing out, and this is some sort of waveform that makes a sine wave at 10 kilohertz, and you go with one increment at a time, how fast are we making the sine wave? And the answer is, well, take the number of samples, which is the wavetable size, which is set up at 200, and divide it into the clock sample frequency, which is 10 kilohertz, right? So 200 samples in the table. I got 10 kilohertz per sample, so I'm clocking out at 50 hertz. That's my lowest frequency I can go with increments of 1. So if I want a frequency I need to jump into the table by an increment that is a function of the frequency. And so if I take the frequency and divide it by 50, because 50 hertz is the increment, if I increment by 1, it's 50 hertz. Then what I do is I take the frequency I want, like 697, divide it by 50 hertz, and now my jump through the table is, well, 13.94, but I have to jump an integer amount, so I round it to 14. So when you go in and look for like this number, 697, it comes out to be 14, right? And so you can do this sort of as an exercise, if you like. 10,000 divided by 50 equals 13.97. You could do the same thing over here. You could take 10,000 hertz divided by sorry, it wasn't dividing by 50, was he? It was the frequency divided by 50. Sorry about that. 697 divided by 50 was 13.97. You can check me on that. And then 770 divided by 50 is some other number, which is probably close to 15. I'll just do a quick check. So 770 divided by 50 comes out to be 15.4. Which is, I don't know, kind of like 15. You're going to see the error, right? If you use 14, that's another way to go. Go back it out. 14 times 50 is going to give me 700 hertz. So I'm going to have an error. So you get 700 hertz with what we've done. And what happens with 15 times 50 is you get 750 hertz. Is it close enough? If it's not close enough, what do I do? How do I make it closer? Any ideas? You know, these things all have error, right? In other words, I don't know what 17 times 50 is. Some number, I suppose. 850. Well, that's pretty close. I mean, 2 hertz off, I can live with that. I think the phone system will be okay with that. And in fact, the demo that this guy runs for his little YouTube video actually shows these things are working okay. So we'll do this, it's 950 instead of 941. How do I make it more precise? Because some of this stuff is going to be off, right? I mean, maybe not by much, but at least as much as 50 hertz. So that's 1200 hertz. Oh, that's pretty good. The most it can be off is like 49 hertz. And this will be, I'm computing this as I go. That's why it's taking me so long. Sorry about that. 1350. Is being off by 49 hertz considered acceptable for the phone system? I don't even know what the tolerance is on that stuff. But 30 times 50 is 1500. So we're getting a little bit further off, I guess. And here's 33 times 50. And that's not going to be exact. 33 times 50 will be 1650. So that's off too. So what's the answer to my question? How do I make this more precise? What I mean, it's a trade-off, right? If you want precision in your frequencies, what will you do?
Could you round it?
Say it again.
Could you round it?
Well, we are rounding. We are rounding. But these are rounding to integers, and we know we're going to be off by 50 hertz. You could be off by only 25 hertz, but how would you do that? Well, you could decrease the size of your wavetable, but then you're not going to have a nice waveform. So instead of a wavetable size of 200, why not do a wavetable size of 100? I guess that's okay. If you clock out a wavetable size of 100 at, I don't know, 10 kilohertz, what does that do for you? $10,000 divided by 100. Does that make it better? And the answer is no, that gives you 100 hertz. That makes it worse. So if I want to make it better, what do? I can increase the wavetable size perhaps by double. So now let's assume I go to 400 samples with 10,000 hertz. And the answer is yeah, that gives me an increment of 25. So that's kind of interesting, right? I could easily change the wavetable size. In fact, if we think about it, we could parameterize these numbers here as a function of wavetable size, right? All these numbers could be a function of wavetable size. And in fact, they really are a function of wavetable size. They're just being pre-computed. So not a bad way to go, really. If you reparameterize it in terms of wavetable size and then double the size of the wavetable, you don't have to recompute everything because all of these numbers can be backed out from the size of the wavetable and your sample rate. Those are the two factors which you have control over. But wait, I just kind of gave it away. What else can I do? I could change my sample rate, right? Let's leave the wavetable alone. Let's change the sample rate by doubling it. I could sample at 20 kilohertz. I think I can. How fast does this thing run? I think it has a maximum data rate of, I don't know, was it 2 megahertz on the, 20 megahertz on the SPI bus. I think that's correct. Let me get rid of this sidebar. Hide sidebar. There we go. Yeah, 20 megahertz. And he says he can do 4.5 microseconds of settling time. So by my reckoning, that's 4.5 times 10 to the minus 6, which I can raise to the minus 1 power and gives me a number of 222 kilohertz sampling. I mean, way, way faster than I need. So going to 20 kilohertz sampling should be a can-do operation for this chip. No problem. No problem. So if we wanted, we could increase our clock rate and leave everything else alone, except that the number of steps that we go through to keep our frequency will have to be adjusted, right? Because we'll be going 25 hertz per step instead of 50, just by virtue of doubling the sample rate. And where would we do that? Well, the answer is all the way down here in the timer area. We have to change how we divide down the Arduino clock to get to 20 kilohertz. And on that note, we could have a nice little lecture about the timer, but I'm gonna spare you that because we have looked at it before, although I do have something prepared. And so that's an interesting point. What else happened in this code as I went through it? Well, I can tell you that this guy was set up to do an R2 ladder, right? So I think we've seen R2 ladders before. For all I know, Dilshane J, say that name for me, J Yakoti, copied his R2 ladder from somewhere else. Guess it's an R2 ladder for DTMF. So this is his R2 ladder, right? And that's a way to make a DAC. I mean, might even be a good way if it's good enough for you and your application. And all the resistors are the same here, and they're all the same up in there, except this doubled that. And other than that, there's a little cap, and that's your DAC. And it takes up like 8 positions worth of output. And so he's writing to positions 0, 1, 2, 3, 4, 5, 6, and 7, which is, I guess that's okay. You can do that. What port is that? 0, 1, 2, 3, 4, 5, 6, 7. Well, I don't know. Let's take a look. And so we can go and we can have a look at digital pin 0. That's port D. 2 is 1, 2, 3, 4. That's all port D. Port D 0, 1, 2, 3, 4. That's convenient. 5, 6, and 7, all port D. Port D, 5, 6, and 7. So that's great. If I have access to port D and a value, I just have to write it out to port D, and it's going to pop out into my resistors. So if we take a look at his code, and this is, very typical of the way people write code nowadays. They just slap in the number they want into the port, and that's their output, and that's it. And so if we take a look at how he does the writing into port D, you can see he said he has identified the DTMF port, and he just sets it up as the output from his wavetable, and that's it. That's all he needed. And if you looked at the DTMF port, I guess it's here in the header file. I think it's here. Yeah, there it is. DTMF port is port D. So that's, where he decided to wire everything because it was convenient. Then all he has to do is set it to some 8-bit number, and it just goes in one end and pops out the other and makes like voltage. And that's it. And certainly you don't need a chip to make a DAC. On the other hand, if you wanted to make a 12-bit DAC, it ain't so easy to do it with this setup because you're pretty much going to use up every single register on the whole thing. But still, it's possible. It's possible. Much nicer to use an SPI DAC. And so I think what we have going for us is far more general, and you don't have to breadboard anything, and just plug it in and off you go. But there is a little overhead in doing that sort of thing, no doubt. Let's see, how else does this thing work? So we got, I added this stuff right in through here, and naturally you could continue doing something like this. Excuse me. Excuse me. And so, oh no, it's COVID. I've been tested. It's okay. I'm safe. So then let's see, what else do we need to know about this thing? I think what happened when I put in my modifications is I became very critical of the guy's code, because these case statements in here, they should have all had sort of regular characters in them, but he did what he did, and that's it. Let's see, what else do we need to know? There's my DAC write. I put that in there, and I wrote it out as a byte. So when you look at the DAC write, it's written as a byte. But if you wanted to reuse this code, you could probably modify it to make use of an int, right? Just break the int up into 2 chunks and transfer them over as 2 bytes instead of doing what I did. Let's see, what else do we need to do? I think that covers it. The rest of this code has not been modified. There's a DAC write output here that's in the wave generator. I think it makes the code cleaner because you can now reuse this code in ways that sort of, I don't know, makes it nice. If you were going to package the code as a library, what you would do is you would rearrange the files a little bit and make a zip file out of it. I'm having a little trouble grabbing the, oh, I got to move this part. Sorry. Zoom gets in the way. So if you went to generate and you said sketch show sketch folder, you can kind of see everything's all in one file, one folder. That's kind of not the way it's supposed to be. Also, the keywords that you want to list in here, you could probably put in some more. Like, for example, DAC. DAC right. I think I got that right, but I'll check. Yeah, DAC right, DAC. Those are my keywords. So then they'll come in colored when next time you want to launch these things. So what I would do if I was going to deploy this as a zip file, and you got to kind of start somewhere. So start with the zip file. And we'll save. Oh, before I save, let's just make sure everything compiles because I don't want to get out of this before I've a chance to undo all the damage I've done. So let's get rid of this too. There. So we'll make a little zip file out of it. And right now I'm in the DTMF Gen Master, whatever. So what I'll do here is I'll make a new folder. I'll call it something like examples. Put in my DTMF generator. And now this part, that has to be turned into a zip file. And I don't have a good way to do that from the command line. I'm not exactly sure how you do that from the I'm sorry, from the graphic user interface. I kind of know how to do it from the command line only. And I kind of think if I go in here and I get info, I could probably get the where part, copy it and close this. And then the next time I bring in my terminal prompt, I can actually CD directly to that location without having to type the whole thing in. So that's convenient. I kind of like that. And then there's this thing in here about the library properties. And I suppose I could include those, but I can choose not to, I suppose, until I'm ready for deployment. But basically, I'm making a copy of somebody else's library, and I do that at least in part because I'm going to branch off and maintain it and do my own thing with it, which is a perfectly legitimate thing to do. Here's the DTMF generate code now with the examples, the keywords, without the library properties. And what I'll do here is I'll make a zip out of it and call it something like foo, because I don't know, I lack imagination or something. DTMF generate, and that just throws everything into the foo file. And then I'll just copy foo.zip over to someplace I can find it. And now I can tell Arduino to load it up as a library. That's how you make a library. It's the simplest thing, really. So let's do sketch, include library, add zip, and go to attachments. I hope this works. I don't do this very often. Date modified. Here's the zip file. Hit choose. And what does that buy you? Well, I don't know. I guess it's called DTMF Gen, right? Something like that. Here it is. And there's the generate code. And it works. And there it is. And now in principle, It's a deployed library, and I can compile it. I don't have to recompile all the ancillary stuff about the DAC and everything, because that's buried in the library. And I don't know what happens. I'm going to just sort of try it, I guess. Does it work? I don't even know. No, I broke it. I broke it. I broke it. I think there may be a conflict because I've done this once before. And so I've overlaid the libraries. Silly me. I should have given it a better name, or maybe a different name. It is supposed to be called DTF generate. Examples. Let's just check it one more time. DTMF. I don't see DTMF generate. I see DTMF gen. Maybe I should have done something with those properties after all. It did seem to load it, didn't it? But it didn't come up. Not as DTMF generate. I think I better do something with the properties and change the name. But that's the general idea. How I screwed it up just now, I don't know quite. But I'll go over that in my own time, and we'll fix that for next time. So yeah, you should be able to, at the very least, get yourself separate compilations so that you don't have to worry about forget about the library for a second. You should be able to do separate compilations. That's for sure. Let's go back into this DTMF generate and see if I can fix what I just messed up. We'll take the examples and we'll move them back. And that should come back. And in principle, it should just work. I mean, this has not been changed that much. And yeah, we're back in business, generating touch tones. So that's the project, such as it is. Any questions? We got a couple minutes left. Does this seem like a reasonable way to break up the DAC? You don't want the DAC to be embedded in the DTMF. You don't want the DAC to be embedded in the DTMF generate. Instead, it is, a separate instance which is used by DTMF, and later, it may be reused by other things as well. So it's at least it's hiding some of the complexity for generating outputs. And it kind of looks like a better way of deploying DAC code, especially if you decide you want to change the DACs later. Because after all, there are other DACs. And in fact, there are better DACs and there's worse DACs. And there's R2 DACs like this. I mean, anybody can make a DAC, or I guess use a DAC. So that shouldn't really be something that should infiltrate into your program. We should be able to hide that complexity. So if somebody later on wants like an I2C DAC, you should be able to plug that in as an instance of a DAC and just start using it in your code without having to rewrite everything and make all these painful changes. Like I just did when I went through and changed from an R2 DAC to an SPI DAC. I mean, that kind of didn't make a whole lot of sense. Later, if I want an R2 DAC and I want to throw that in there, I should be able to. So that's that's my take on the software engineering on this project. It needed a little bit of work, some attention. So that's another reason why you might want to branch it and turn it into something that looks a little bit closer to an object-oriented program than whatever it was he was doing with ports. Does that kind of help people a little bit with the project? So all this is being recorded, so you can watch it again if you like. And that's what I have for you for today. I hope you guys are safe. I think there's almost 600 infected people on campus now, so I'm staying far away. Enjoy your break, and thank you.
You
for your
too.
time.
Thank you, Professor.
Thank you, Professor.
Thank you. Bye-bye.